For this next lesson, we're going to look at what happens when you want to take the derivative of a function that is made up of the product of one or more functions. So we are going to look at two rules and then look at some examples of how we can use those rules. So the product rule states that if you want to take the derivative of f times g of x, so if you're taking f times g prime, it's not just equal to f prime times g prime, it's actually equal to f prime times g plus g prime times f. So you take the derivative of one and multiply it by the original function of the other, plus the derivative of the other function times the original function of the first function. Okay, so let's look at a fairly simple example. If we have f of x equals 3x squared and g of x equals 2x to the fourth. Okay, so we're going to do f times g prime. Okay, so let's look. F prime is equal to 6x. G prime equals 8x to the third. So those are our derivatives. So f times g prime is equal to f prime g plus g prime f. So that is equal to 6x times g, which is 2x to the fourth, plus 8x to the third, which is g prime, times f, times 3x squared. Okay, so when we go ahead and we multiply everything through, we get 12x to the fifth plus 24x to the fifth, which is 36x to the fifth. Now, in this case, we could have done this in an alternate way. So f times g, we could have just computed f times g of x, which is equal to 6x to the power of 6. Okay, because when we multiply 3 times 2, we get 6. X squared times x to the fourth is x to the 2 plus 4, or x to the sixth. So here we would also get, if we check it another way, fg prime of x equals 36 times x to the fifth. So we can actually check that this method of doing it works out. And you can see if we just multiplied the two f prime times g prime, we would not get the same answer. Okay. So it is possible to do these problems. Sometimes you can just multiply the functions and do it without using the product rule. The product rule often exists for times when we can't do that, or when doing the multiplication would be sort of prohibitively difficult. So let's take a look at one of those problems. So if we have f equals, so let's find f prime. This is our second example. Find f prime of x for f of x equals fourth root of x times x to the minus 2 plus x cubed. Okay, so this is equal to g times h, so this is, so f prime of x equals g prime h plus h prime g. Okay, so let's make our first function g equal x to the power of 1/4. So g prime is 1/4 x to the negative 3/4. And h is equal to x to the minus 2 plus x cubed. So h prime is negative 2x to the minus 3 plus 3x squared. We're again using our power rule to get all of these. So if we want to just give an answer without trying to simplify too much, we can say that f prime of x is equal to g prime, so 1/4 x to the minus 3/4 times x to the minus 2 plus x cubed plus h prime, which is negative 2x to the minus 3 plus 3x squared times g times x to the 1/4. Okay, and it would be possible to expand the brackets if we like, but in this case, it's probably not necessary. Okay. So the next rule is the quotient rule, and the product rule, as you can see, it's not too difficult to use. The quotient rule, things can get rather complicated rather quickly, so it is better to avoid using the quotient rule if you possibly can. So our quotient rule is f over g. Okay, if we want to take the derivative of f over g, the quotient of two functions, that is equal to f prime times g, this time minus g prime, times f over g squared. So you notice in the product rule, the order didn't matter too much. It was the derivative of one times the function of the other plus the derivative of the other one times the function of the first. Here the order does matter, so it matters which one is in the numerator. So you're taking the derivative of the numerator divided by the denominator. So it's the derivative of the numerator times the function in the denominator minus the derivative of the denominator times the numerator all over the denominator squared. So I believe one of my student teachers had a lovely way to remember it, which is low d high minus high d low, square the bottom, and there you go. Pretty cute. So let's look at an example of where we might use the quotient rule. So the first thing to note, so we have 3x squared minus x over x cubed plus 1. Okay, and we want to find the derivative of this. So clearly this does not divide, so there's no division we can do in order to deal with this without using the quotient rule, because that would usually be our first choice. So I like to write out f is 3x squared minus x, f prime is 6x minus 1, g is x cubed plus 1, and g prime is 3x squared. Now you don't necessarily need to do this every single time as you get accustomed to the quotient rule, but I find it useful when I'm first starting out to do this. So low d high, so d high is 6x minus 1 times x cubed plus 1 minus high, which is f, 3x squared minus x, d low times 3x squared, and square the bottom. And there you go. So that's x cubed plus 1 squared. And again, unless you're asked to simplify, I would probably leave this just like that because it's quite unlikely that you're going to get a nice x cubed plus 1 that's going to drop out. So let's look at another one that might be, so if we have so let h of x equal 4x cubed minus 2x to the minus 2 plus radical x all over x. So we have a function here. Now, my favorite thing to say about the quotient rule is your best bet with the quotient rule is if it's at all possible, try to avoid using the quotient rule. So as long as we only have powers of x, whether they're positive, negative, or fractional, we can use our power law that x to the a over x to the b, as long as we have a single term in the denominator, and that's a good clue to look at, is equal to x to the a minus b. And that works for fractional powers, it works for negative powers. So we just subtract the exponent on the top from the exponent on the bottom. As long as we have a single power of x down there, we can rewrite this as 4x cubed over x. Okay, our goal is going to be to find h prime of x. Okay, so h of x is also equal to 4x cubed over x minus 2x to the minus 2 over x plus, we're going to rewrite radical x as x to the 1/2 over x. So these are all x to the 1. So we're just going to be subtracting that exponent of 1. So h of x is equal to 4x squared minus 2x to the minus 3 plus x to the 1/2 minus 1, which is x to the negative 1/2. So we notice now there's no longer a quotient. So I actually don't have to use the quotient rule. So I can just go ahead and use the power rule. So h prime of x, and notice I go from writing h of x to writing h prime of x. It's pretty important to differentiate when I'm actually taking the derivative. So I get 8x minus 3 times minus 2 is plus 6, x to the minus 4, plus negative 1/2 x to the negative 3/2. Negative 1/2 take away 1 is negative 3/2. And if I want to rewrite it using the notation we originally have, I have 8x plus 6 over x to the 4th. Notice here, this is a common mistake. We've got 6 times x to the minus 4th. Exponents happen before multiplication by our order of operations, so the 6 stays on top. Plus negative 1/2 x to the negative 3/2, so that's going to be minus 1 over 2 radical x cubed. And so as I said, the quotient rule is great, but if you can avoid using it, it's highly recommended. Let's look at one more example where we can't avoid using the quotient rule. So let's see, find h prime of x for h of x equals 2 over x plus 1. So clearly here, we're not going to be able to divide the 2 by x plus 1. And this happens a lot when you have more than one term in the denominator. Unless you can divide everything by it, you are going to have to use the quotient rule. So let's make this f and this g. So we have f equals 2, f prime equals 0, g equals x plus 1, g prime equals 1. So we have some relatively simple numbers. So h prime of x is going to equal low d high, which is 0, minus high, 0 times x plus 1 is still 0, times high d low, square the bottom, and there you go. So this is equal to negative 2 over x plus 1 squared.